Hello and welcome to the second course in physical chemistry. I'm Dr. Gor Sarkisian and we will begin the course with Introduction to Quantum Theory. In this lecture, we will go over energy quantization, the wave-particle duality, Schrodinger's equation, the Born's interpretation of wave function, operons, superimposition of expected values, and so on and so forth. So without further ado, let's begin. The classical mechanics predicts that characteristics of a particle such as its location, momentum, trajectory can be known at any given time. Furthermore, it allows for the translational, rotational, and vibrational modes to be altered by simply applying force. And these conclusions hold true in everyday experiences. However, they do not hold true when it comes to individual atoms. The classical mechanics altogether fails when it has to do with small energies and small masses altogether. Let's begin by examining several noteworthy experiments that were conducted at the end of the 19th century that led scientists to believe that the energy can be transmitted only in discrete amounts. The first, we will examine the black body radiation. What is black body radiation? Well, it is basically when an object is heated, it can emit an electromagnetic radiation. A metal, for example. A hot metal can radiate in a visible spectrum. And when we talk about hot metal, we see it as yellowish, reddish, glowing rod, right? But if we keep heating the rod up, it actually starts emitting electromagnetic radiation or wavelengths that are closer towards blue. So therefore, it starts emitting light that is closer to being white. On this graph, we have several representative curves of what's called a black body emitters. Black body emitter is basically an object that is that can emit and absorb all wavelengths of radiation uniformly. Now, the take-home message here is that as energy distribution increases, the wavelength of radiation decreases. Now, decrease of wavelength means that at any given point, the quanta that, or a wave that is emitted by the black body is of higher energy. There is a reciprocal relationship between the wavelength and the energy of the photon. A fairly straightforward model of black body is basically an empty box with a pinhole. And any radiation that leaks out of this pinhole is basically in thermal equilibrium with the container because it has bounced in this container so many times that the radiation is quite characteristic to this particular container. Now, to model this, the 19th century scientists derived an equation in which the energy emitted, the delta E, is rho, that is a function of lambda and temperature, times delta lambda, okay? And rho is generally known as the density of the state, and it's represented as joules per meter to the fourth power. So why is there a delta lambda? Because this black body will have lambda plus some delta lambda wavelengths that can create a full isolation within this container. Basically, this container will hold so many different wavelengths that have full oscillation within this container. So if we want to find the total energy, that is, or total energy density, we have to take the integral of everything that is within this that contributes to this energy. So energy as a function of t equals an integral from 0 to infinity. We have to incorporate everything. Rho lambda t delta delta lambda. This is in agreement with the observation that it depends on the temperature in such a way that higher temperature results in greater energy. So basically, the total energy within the region of volume V is the energy density multiplied by its volume. So quite simple. So energy T is volume times energy at that T. That's it. Relay, in turn, thought that the electromagnetic field is a collection of oscillators of all possible frequencies. He regarded the presence of radiation of frequency mu as signifying that there is electromagnetic oscillator of that frequency that is in existence. So what does that really mean? If we have, let's say this is frequency 1, then we have an oscillator in which the wave, an n number of wave would fit within this oscillator, and n is always an integer, right? So there is another wave that is n number of waves, which is also an integer. So this oscillator can potentially have many different waves in it, which are within still the resonance system. So really knew of the fundamental principles such as equipartition principle, which shows that thermal equilibrium, any degree of freedom which appears only quadratically in energy has an average energy of half of kBt, or kt in this case. So it attributes only half of k to the heat capacity. So he derived the rho value to be lambda t, which equals 8 pi kt over lambda to the 4th power. And of course, k here is the Boltzmann constant, and it's 1.381 times 10 to the minus 23rd joules per Kelvin. Even though the Rayleigh-Jeans law is quite successful in long wavelengths, it does not hold true, or rather fails, when it comes to shorter wavelengths. That's when lambda decreases, our rho increases, right? However, this corresponds to short wavelengths, the ultraviolet radiation X-ray, which are strongly excited even at room temperature. Therefore, if we remember the earlier shown formula in which energy at a given temperature is an integral of 0 to infinity, rho lambda t delta lambda. He is also basically predicting that at temperatures that are above zero, the total energy density must be infinite. It is somewhat an absurd result. Well, not somewhat. It is an absurd result because this implies a large amount of energy is radiated in high frequency regions. And this absurdity, shall we say, is known as ultraviolet catastrophe. Well, why is this a bad thing? Well, if you think about it, according to classical theories, physics, even cold objects should radiate in a visible and ultraviolet radiation. Therefore, the object should glow in the dark. And what does that mean? For practical purposes, that means that there should be no darkness altogether. Go figure. Even though similar to Rayleigh-Jean's law, the Planck's law also, or Planck's calculations also include some very important exponents in a denominator. Well, basically, for short wavelengths, the correlation is as follows. Hc over mu kt is much, much more than 1. And the exponent of Hc lambda kt, therefore, approaches infinity. It approaches infinity faster than lambda to the 5th power approaches 0. Therefore, rho also approaches 0. And as lambda approaches 0, obviously, the frequency approaches infinity because of its inherent reciprocity. So this relationship basically calculates very well this observed curve. Now, for wavelengths that are longer, the Hc divided by nu kt is much, much less than 1, right? And the following, the denominator of the Planck's distribution can be now rewritten as such. The exponent of Hc divided by lambda kt minus 1 is now it will equals to 1 plus Hc divided by lambda kt plus yada 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 minus 1, which then equals roughly to Hc lambda kt. There we go. The most important thing is if this approximation is inputted into the Planck's distribution, which is rho lambda t, which equals to 8 pi Hc divided by lambda fifth exponent Hc divided on lambda kt minus 1. If we include this approximation into the Rayleigh distribution, we actually get the Rayleigh-Jeans law. Now, let's write this out in a more legible way. Let me open up a new page. So let's go over it again. The Planck's distribution. The Planck distribution is the rho lambda t equals to 8 pi hc divided by lambda fifth exponent of hc divided by lambda kt minus 1. Okay? So if we take the approximation that we calculated in the previous page, which was, if you remember, an approximation of hc divided by lambda kt, if we take this and integrate it into the previous equation for energy, the ET, then we get an integral of 0 to infinity 8 pi hc divided by lambda lambda to the fifth power ehc divided by lambda kt minus 1 delta L, which equals basically an AT with A being this A being 8 pi fifth K fourth divided by 15 HC to the third power. Therefore, the energy distribution increases by the fourth power of the temperature. Sorry, there is a fourth power to the temperature here. So let's demonstrate the take-home message by solving a problem of black body radiation of two incandescent light bulbs, one operating in the blue at 450 nanometers, the other one operating in the red at 700 nanometers. And all of this is happening at room temperature, 298 Kelvin. So at a given temperature T, the ratio of spectral densities of the state at the wavelength L1 to L2 is as follows. The rho of lambda 1T divided by rho lambda 2, there is a one here, T equals to the ratio of these two wavelengths, lambda 2 over lambda 1 to the fifth power, times the exponents, the Planck's exponents, which is EHC divided by lambda 2kt minus 1 divided by, obviously, EHC divided by lambda 1, sorry about that, kt minus 1. Okay? So from this point on, we have to just substitute and solve for our ratio here. So basically, we have to do our regular computations here. And we use 450 for lambda 1, 700 for lambda 2. So we have the HC divided by lambda 1 kt, which is, of course, as we noted, the 6.626 times 10 to the minus 34 joules per second times speed of light, c, which is 2.99 times 10 to the 8 meters to the minus meters per second, sorry. And we divide all of this but by our 450 well, times to the minus 9 meters, right, a nanometer, and we multiply it by the K, which is 1.381 times 10 to the minus 23 Kelvin, joules per Kelvin, and we'll multiply that by our T, which is 298 Kelvin, right? So, in short, for a wavelength of L, the wavelength of lambda 1, which our case is 450 nanometers, it's 107.2. Lambda 2, which is 700 nanometers, it's 68.9. Okay? And therefore, we can do the ratio, which is rho of 450 nanometers at 298 Kelvin over rho 700 nanometers over 298 Kelvin. And this equals to, let's open up another page. From our initial equation, it equals to 700 times 10 to the minus 9 meters divided by 450 times 10 to the minus 9 meters. All of this into the fifth power times, now we have calculated this already, so e to the 68.9 something minus 1 divided by e to the 107, 107.2 something minus 1. And in short, this equals to this component, which boils down to 9.11, multiplied by this component, which is 2.3 times 10 to the minus 17. Therefore, that equals to 2.1 times 10 to the 16. Okay? And again, the overall formula is rho of lambda 1 at T divided by rho lambda 2 at T equals the ratio of lambda 2 divided by lambda 1 to the fifth times e to the hc divided by lambda 2 kt minus 1 divided by e to the hc divided by lambda 1 kt minus 1. Of course, this is minus 1 from this exponent. Okay? So that's it. That's the cardinal take-home message here. The next energy quantification is heat capacity. So in mid or early 19th century, French scientists DeLong and Petit determined that heat capacity CV equals internal energy divided by the temperature at constant volume. Okay, so they basically roughly determine that for monoatomic elements, molecular heat capacity is the same, and it equals to 25, well, roughly equals to 25 joules per Kelvin mole. So this law is actually somewhat easily justified. So in classical physics, we validate the equipartition principle using or infer that by inferring that the mean energy of an atom is as it oscillates about its mean position is kT, right? And it's kT for a single direction, but electron obviously can oscillate in 3 dimensions, so it's actually, well, in 3 dimensions, so it's actually 3 kT. All right, and the total energy is, well, total number of electrons times kT, so 3 for the 3 axes, and for the number of electrons, and kT. Now, the funny thing is, nkt is actually gas constant. This is Planck constant, and as you know, Planck's constant and gas constant are synonymous to each other. They're just used in different systems. So in reality, the capacity equals to 3R. So 3R is roughly 24.9 joules per Kelvin mole. Okay, very interesting, but unfortunately, with advanced heat measurement techniques, it was shown that heat capacity of all monoatomic solids is actually lower than 3K when the temperature approaches 0. So what happened? In 1905, Einstein decided to perhaps let's try to apply Planck's hypothesis to this phenomenon and see what happens. So basically implying that the vibrations are also limited, and again the NH mu, it holds true here also, and N is an integral constant. So basically, Einstein derived the following, that CV m equals, as a function of t, equals 3r function of energy of t, and a function of energy as a function of t equals a number that is known as Einstein temperature divided by T squared times exponent of this component divided by 2T over exponent of Einstein's temperature component divided by T all minus 1 squared. So this is known as Einstein formula. So the Einstein temperature equals to H mu over K. So it's this constant. So this is just a way to express the frequency of oscillation of the atom as a function of temperature, and basically allows us um, to quantify the mean value by basically high temperature, which is much higher than the Einstein temperature, and something that is much lower than Einstein temperature. In this context, the high vibrational frequencies correlate to high Einstein. Now let's write the phi value here also again, and look at what happens when the T is much larger than the Einstein temperature. So when we have our expression here, which is Einstein's constant divided by T squared times 1 plus Einstein constant over 2T divided by 1 plus Einstein constant divided by T minus 1. So when T is extremely large, right, this term approaches 1, and this term also approaches 1. Therefore, this whole thing becomes very close to 1, right? So remember, we had the heat capacity that was that as a function of T that equaled 3R phi T. Now this component is 1. Therefore, at high temperatures, we obtain our initial 3R, which is in complete correlation with the Perrier-Dulac and Petit calculations. And again, as we stated earlier, this is only true for high temperatures. But at low temperatures, the same expression roughly equals to Einstein temperature over T squared e to the negative Einstein temperature over T. So this is another equation to remember. I will send you a synopsis of all of the important equations that are going to be important in exams and in final and in the quizzes. So all in all, Einstein's formula accounts for the decrease in heat capacity at low temperatures. Its physical explanation is that at low temperatures, only a few oscillators possess enough energy to oscillate significantly. So for practical purpose, few atoms are actually available. But at high temperatures, practically all of the electrons contribute to this heat capacity. Here we have a graph that visually shows the dependence of the heat capacity by the Einstein's formula. The shape is satisfactory, but as you can see, the numerical values are off, are in a poor agreement. This is because Einstein's assumption that all elements oscillate at the same frequency. But in reality, as they isolate at a range of frequencies from 0 to some maximum um, mu d. And so this is a result of averaging. So another equation was necessary to account for this, and this equation was derived by dBay. So in this case, the heat capacity equals to 3R phi d t. Very similar, but we account for everything here. So the phi d in this case equals, or as a function of t, equals 3 t over a similar term as Einstein's temperature to the third power, and then integral of phi over t of x to the fourth power e to the x power divided by e to the x power minus 1 squared dx. And this is another formula to remember, and it's dBay formula. Here, this term, the phi d, equals to h mu d divided by k. Similar, but we're taking in consideration slightly different frequency range, similar to that of Einstein's, but in this case, it's called the dBay temperature. Now, the integral part, we need not worry about that. That portion is calculated through current mathematical methods by computers very well, and basically we don't need to derive it. So all in all, the dBay's modification of Einstein's calculations correlate almost perfectly with the data obtained. So good news. So all in all, the take-home equations here are the Einstein formula, which is CVM of T equals 3R Fe of T. Now Fe of T in turn equals to the ratio of Einstein temperature over actual temperature squared multiplied by E Einstein temperature divided by 2T, all of it divided by E to the Einstein temperature divided by T minus 1 squared. Now, for temperature that is much higher than Einstein temperature, this whole thing becomes practically 1. So this is, therefore, this is the contributing portion. The other important formula to remember is the dBay formula, and it's CV m of t equals to 3r fd of t, right? So the cardinal difference here is that the fd equals to 3 times temperature over specific or debate for a temperature cubed, integral of 0 to debate temperature over T x to the fourth power Ex divided by Ex minus 1 squared dx. Of course, I will not ask you to solve such problems, but I may ask you to calculate, for example, debate temperature, which is fairly straightforward, and it equals to h mu divided by k. And with this, we will conclude today's lecture, and we will pick it up with the atomic and molecular spectra. Thank you.